Welcome to this A-Level Maths Core 2 preparation video. We're going to recap Chapter 2 of the C1 module, which was all about quadratic equations. But before we do that, I'd like to tell you a short story. 27 seconds. A man is sitting on a motorbike facing east. 9 seconds. A man is doing a handstand and his motorbike is about 10 metres in the air. 17 seconds. The motorbike is on top of the man and he's upside down. 13 seconds. A man is sitting on a motorbike facing south. 37 seconds. Some people are waving white hankies in the air. 5 seconds. A man is sitting on a motorbike facing west. 23 seconds. A man in a blue shirt leans forward. 10 seconds. A man is sitting on a motorbike facing west. Okay, that wasn't a great story. It tells you about things in the wrong order. It leaves lots of events out. It leaves out a lot of detail and context even for the events that it does cover. You aren't left with a very clear idea of what happened. There's a saying that a picture is worth 1,000 words, so imagine how many words a video is worth. Watch this.
And just watch this kid, watch the extension he gets, and look at how flexible he is. We need to get the side angle on that, because that is a trick thrown only by Levi Sherwood. Heel flicker. Oh, nice. So he's stepping it up a little bit. He's changed his run-up already and powering through the corners a bit. What I can't believe is that the pressure does not seem to be getting to him. He hasn't done many big contests, but he has done a lot of shows for a lot of crowds in Australia and New Zealand.
Now that was about the same length as the story, but you're left with a much clearer idea of what was going on. Believe it or not, quadratic function sketches are like X-Fighter video clips. They're capturing a whole bunch of important details about the relationship between two variables and presenting them to you in a succinct and easily digestible format. An equation is effectively a list of things to do with an input, x value, to arrive at an output, y value. A graph is simply a systematic process of trying out a load of different inputs, calculating the corresponding outputs, and plotting them so they're easy to see. They give you a visual representation of how y outputs vary with changes in x inputs, and tell you when important moments of action occur, when the curve crosses the axes or turns around. So many things behave in ways that can be approximated by quadratic functions that this turns out to be a really useful branch of mathematics. That's why you spent so long in GCSE factorising, using the quadratic formula and solving quadratic equations. Cars skidding and crashing, parallel resistors in an electronic circuit, and cricket balls flying through the air all behave quadratically. The efficient use of resources for packaging requires quadratic equations. Satellite dishes are designed using quadratic curves, and even the chaos in changes in annual bee populations can be analysed using quadratic equations. Showing when the curve turns, the maximum or minimum point, or where it crosses the axes is important because it can tell us about key aspects of the problem being modelled by the quadratic equation. It might tell us when a falling object will hit the ground, or a chemical reaction will run out of catalyst, or the optimum length for a cardboard box so it can use as little card as possible for a given volume. You might remember from GCSE that the general equation for a straight line is y equals mx plus c, where m tells you the gradient of the line, how much the y value increases every time you increase the x value by 1, or for every extra 1 you put in, how much does the output change. Then, if you input a value of 0, so x equals 0, this makes the y coordinate m times 0, which is 0, plus c. So the value of c tells you the y coordinate when the x coordinate is 0. In other words, where the line crosses the y-axis. Obviously, straight lines are, well, straight. This means that if you increase the x value by 1 anywhere along the x-axis, the corresponding y-coordinate always goes up by the same amount, m. For example, if y represented the fare charged by a taxi driver, then a straight line graph would mean that every extra mile you want to travel will cost you the same extra amount m, whether it was the first mile you travel or an extra one after driving twice around the world. The rate of change of fare stays constant regardless of the distance you've already covered. We can look at the general equation for a quadratic curve in a similar way. Y equals ax squared plus bx plus c. We can get all fancy and we can call it a polynomial of order 2, or we can say that it's just something times x squared plus something else times x plus a number. Know that it can't have any other powers of x and it can't have anything over x. Again, the c tells us where the curve cuts the y-axis, because inputting an x value of 0 means we'll get 0 times a plus 0 times b, and then y will just be equal to whatever c was. Quadratic curves are not straight. They're all symmetrical parabolas, basically smiley mouths or sad mouths on the graph. They stretch all the way from x equals negative infinity to x equals positive infinity. You can input any x value at all. But the y values you get don't stretch out all the way from negative infinity to positive infinity. They'll get to one of them, but because the curve stops and turns around somewhere, they don't make it all the way to the other y extreme. Some of them cut through the x-axis in two places, some of them touch it in one place, and some of them don't make it to the x-axis at all before turning round and heading back to negative or positive infinity. Let's look at some specific quadratic curves and make some general points about values of a, b and c. Y equals 0.1 x squared plus 3x minus 2, and y equals minus 0.1 x squared plus 3x minus 2. Y equals 0.5 x squared plus 3x minus 2, and y equals minus 0.5 x squared plus 3x minus 2. Y equals x squared plus 3x minus 2, and y equals minus x squared plus 3x minus 2. Y equals 2x squared plus 3x minus 2, and y equals minus 2x squared plus 3x minus 2. Y equals 3x squared plus 3x minus 2, and y equals minus 3x squared plus 3x minus 2. You can see that when a is positive, then you get a positive happy smiley curve, and when a is negative, you get a negative sad curve. You can also see that the closer a is to 0, the fatter the curve, and the larger the magnitude of a, the thinner it gets. Now, here are some more quadratic curves. Y equals x squared plus 3x minus 3. Y equals x squared plus 3x minus 2. Y equals x squared plus 3x minus 1. Y equals x squared plus 3x plus 0. Y equals x squared plus 3x plus 1. Y equals x squared plus 3x plus 2. Y equals x squared plus 3x plus 3. All we changed was the value of c, and you can see how that affects where the curve cuts the y-axis. Now look at these quadratic curves. Y equals x squared plus x minus 3. Y equals x squared plus 2x minus 3. Y equals x squared plus 3x minus 3. Y equals x squared plus 4x minus 3. All we changed was the value of b, and as we made it bigger, the curve moved left. But note how the basic shape, fatness, and where the curve crossed the y-axis didn't change. Let's see what happens when we decrease the value of b. Y equals x squared plus 4x minus 3. Y equals x squared plus 3x minus 3. Y equals x squared plus 2x minus 3. Y equals x squared plus x minus 3. Y equals x squared plus no x minus 3. Y equals x squared minus 1x minus 3. Y equals x squared minus 2x minus 3. Y equals x squared minus 3x minus 3. Y equals x squared minus 4x minus 3. It moves the curve to the right. But wait, it's not quite as simple as that. Look at these. Y equals minus x squared plus x minus 3. Y equals minus x squared plus 2x minus 3. Y equals minus x squared plus 3x minus 3. Y equals minus x squared plus 4x minus 3. So when a is negative, increasing b moves the curve to the right. Decreasing b moves it to the left. Y equals minus x squared plus 4x minus 3. Y equals minus x squared plus 3x minus 3. Y equals minus x squared plus 2x minus 3. Y equals minus x squared plus 1x minus 3. Y equals minus x squared plus 0x minus 3. Y equals minus x squared minus 1x minus 3. Y equals minus x squared minus 2x minus 3. Y equals minus x squared minus 3x minus 3. Y equals minus x squared minus 4x minus 3. You saw how to factorise quadratic equations and complete the square in your C1 preparation videos, so we won't go through those again now. But you can put all these skills together to help you to sketch quadratic curves. For example, sketch the curve y equals x squared plus x minus 6. Well, a is 1, b is 1, c is minus 6. It's a positive, happy curve because a is positive. It cuts the y-axis at minus 6 because c is minus 6. That means it must cut the x-axis in two places, but it's not immediately obvious where the minimum will be. Will it be to the left or the right of the y-axis, or on it? Now, you can quickly tell if you work out the value of minus b over 2a. That gives you the x-coordinate of the minimum or maximum point on a quadratic. We don't expect you to remember that, by the way. If you've learned about differentiation yet, you can differentiate the general quadratic formula and use it to work out when the gradient of the curve is equal to 0, i.e. the minimum or maximum point. This is the result. So in our case, minus b over 2a is equal to minus 1 over 2 equals minus a half. So the minimum is to the left of the y-axis, so the curve will look something like this. Now we need to know exactly where it cuts the x-axis, i.e. where the y-coordinate is 0. X squared plus x minus 6 is equal to 0. But this factorises to x plus 3 lots of x minus 2 equals 0. And the only way to get an answer of 0, if you multiply two things together, is if one of them is 0 itself. So either x plus 3 equals 0, which would mean that x equals minus 3, or x minus 2 equals 0, which would need x to be equal to 2. So marking these on our sketch, we get this. By the way, because quadratic curves are always symmetrical parabola, if you know the two places the curve cuts the x-axis, then the minimum or maximum will be exactly halfway between them. So you don't need to remember the minus b over 2a thing. Now here's a plea from maths teachers and exam markers all over the world. Please remember to label your axes and mark on these important bits of information, or we can't give you full marks in the exam. Okay, let's look at another example. Sketch the curve y equals x squared plus x plus 6. The more eagle-eyed among you will have spotted that this is very similar to the last one. Well, again, a equals 1 and b equals 1, but now c equals positive 6. It's a positive happy curve because a is positive. It cuts the y-axis at positive 6 because c is 6. So the big question in this case is how far down does the curve go? Will it go low enough to reach the x-axis, or will it turn around and start increasing again before it cuts the x-axis? Okay, so there's another big question too. Will the minimum be to the left or right or on the y-axis? I'm guessing that some of you have thought of a third big question along the lines of who cares? If that's the case, then I've got a fourth big question for you. How do you keep someone who isn't interested in maths in suspense? Well, we'll come back to both of those two in a later video. If the curve goes low enough just to touch the x-axis in one place, then obviously that point will be the minimum. If it cuts it in two places, then the midpoint of those two will give you the x-coordinate of the minimum. The answer to the first big question can help us to find the answer to the second big question. The problem is, though, if the answer was it doesn't go down low enough to cut the x-axis, then it makes it a bit harder to find where the minimum is. We could either use our minus b over 2a formula, if we can remember it, or we can complete the square. I've just thought of another big question. How do we know if the curve goes down low enough to cut the x-axis? Well, you probably remember from GCSE that we made you spend ages solving quadratic equations that were equal to 0. There were several ways to do it. Your maths teacher probably made you factorise the equations like we did in the first example, and use the fact that the only way to get 0 if you multiply two things together is if one of them is 0. This is generally agreed to be pretty neat, until you discover that some quadratics are really hard to factorise, and some others are actually impossible. Your maths teacher probably also went on a lot about completing the square to solve the equation, and it's generally agreed that maths teachers think that this method is pretty neat. You also learned about something called the quadratic formula, which comes about by applying the completing the square method to the general formula of a quadratic equation. It takes about a page and a half of working out to end up with the formula x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a, when ax squared plus bx plus c equals 0. And that probably frightened the bejeebies out of you at first, and made your maths teacher feel a little bit smug, because they understood it and you didn't. The weird thing is that when you use the formula a few times and realise that it was just a matter of whacking a few numbers into your calculator, you probably abandoned all other methods altogether and decided that the formula was the prettiest, neatest method of all for solving quadratic equations which equals 0. What you might not have noticed is that all these methods are about finding out if and where a quadratic curve cuts the x-axis. They're all ways to find the x-coordinates when the y-coordinate is 0. The reason it's also complicated is that sometimes there are no x-coordinates which generate a y-coordinate of 0, because some quadratic curves don't cross the x-axis. If we take a look at the quadratic formula again, notice that we're trying to find the square root of b squared minus 4ac. This value has got a special name, the discriminant, and it determines whether the curve cuts the x-axis in two places, one place, or not at all. The x-coordinates of the points where a quadratic curve cuts the x-axis are called the roots of the equation. The roots are not to be confused with square roots, by the way. Because the quadratic formula requires you to find the square root of the discriminant and then add or subtract it to another number to find the roots of the equation, several things can happen. If b squared minus 4ac is bigger than 0, then there'll be a positive and a negative square root to use in the rest of the formula. So it will generate two distinct roots and means that there are two places where the curve crosses the x-axis. For example, with the curve y equals x squared plus 2x minus 15, a is 1, b is 2, and c is minus 15. So b squared minus 4ac is 2 squared minus 4 times 1 times minus 15, and 4 plus 60 is equal to 64. 64's got two square roots, 8 and negative 8. That means the formula gives us x equals minus 2 plus 8 over 2 times 1, which is 3, or x is equal to minus 2 minus 8 over 2 times 1, which is minus 5. So that curve gives us two places where it cuts the x-axis, x equals 3 and x equals minus 5. If b squared minus 4ac equals 0, then there'll be a single square root of 0 to use in the rest of the formula. This means that we'll add 0 and subtract 0 from something else, and it will generate just one unique root, and means that there's just one place where the curve touches the x-axis. For example, with a curve y equals x squared plus 2x plus 1. A equals 1, b equals 2, c equals 1. So b squared minus 4ac is 2 squared minus 4 times 1 times 1. That's 4 minus 4 equals 0. So 0 has just got one square root, 0. This again means the formula gives us minus 2 plus 0 over 2 times 1, which is minus 1, or x equals minus 2 minus 0 over 2 times 1, which is again minus 1. So that curve gives us one place where it touches the x-axis. If b squared minus 4ac is less than 0, then there won't be any real square roots of the discriminant, because I can't multiply anything by itself to get negative answers. Two positive numbers multiplied together will make a positive answer, and two negative numbers multiplied together will also make a positive. So we've got an impossible situation. There aren't any x values which generate a y coordinate of 0 in the equation. No real roots. The curve doesn't touch the x-axis. I know this video is almost unbearably long already, but I feel I have to give you just a quick explanation of why I've started dropping the word real into the conversation at this point. As if mathematicians weren't smug enough already about the things they thought were pretty neat, they decided that although there isn't actually a number which can be multiplied by itself to give a negative answer, they would pretend there was. These square roots of negative numbers have been named imaginary numbers. I know, it's ghastly, isn't it? Blame Heron of Alexandria, Raphael Bombelli, Girolamo Cardano, Leonhard Euler, and Carl Friedrich Gauss for suggesting, divining, developing, and popularising the idea. On the bright side, it made the maths behind the electronics which produce your MP3 player a lot easier, and the square root of negative 1 seems to crop up in loads of places, from quantum physics to an equation which describes something we call the normal distribution, something that's inextricably linked to almost everything on the planet. Now, where was I? Oh yes, we were trying to sketch the curve y equals x squared plus x plus 6, and we got as far as saying it was happy and cuts the y-axis at 6. We wanted to know if it was going to come down as far as the x-axis. Well, a equals 1 and b equals 1 and c equals 6. So b squared minus 4ac is 1 squared minus 4 times 1 times 6. That's 1 minus 24, that's minus 23. That's negative, so no, it doesn't reach the x-axis. So does it go down to the left, right, or on the y-axis? Well, minus b over 2a is minus 1 over 2 times 1, which is minus a half. So the minimum is at x equals minus a half. So it's to the left. Let's pop x equals minus a half back into the original equation and see how low it goes, the y-coordinate of the minimum point. Well, y is minus a half all squared plus minus a half plus 6, which is 5 3/4. So the minimum is at minus a half, 5 3/4. There, all done, sketch complete. Nah, you're forgetting something. I'm a maths teacher. I think that completing the square is pretty neat, remember. I'm going to find the minimum that way too. Well, y equals x squared plus x plus 6, or to put it another way, y equals x plus a half all squared minus a quarter plus 6. So y is x plus a half all squared plus 5 3/4. So our y-coordinate is something squared plus 5 3/4. Now, given that something times itself always gives a positive number, in the real world anyway, how small can we make y in this equation? Well, the smallest we could possibly make it is if the thing that's squared was 0, because that can't go any lower. In other words, if x plus a half is equal to 0, which would mean x is equal to minus a half. So when x is minus a half, then y would be 0 squared plus 5 3/4. In other words, y would be 5 3/4. Yeah, same as before, but that's reassuring, not boring. That's pretty much all there is to know about quadratics in C1 then, but before we go, let's look at an example which relates to a real-world situation. Imagine we've got a square sheet of card, 100 centimetres by 100 centimetres, and we're going to cut out the corners and fold up the sides to make a square-based container. We could snip out a small amount to make a very shallow box, or we could snip out a larger amount and make a smaller based, taller box. If we let x be the length of the corners we cut out, we can build an expression to tell us the area of the card that will be used. The length of the side is 100 centimetres, this is x, so the width of the base must be 100 minus x minus another x, or 100 minus 2x. Since we're making a square-shaped box, the same is true in the other direction. That means the area of the base is 100 minus 2x times 100 minus 2x. Each side flap is 100 minus 2x wide and x high, so its area is x times 100 minus 2x. There are 4 side flaps, so the total area, when we add it all together, is 100 minus 2x all squared plus 4x lots of 100 minus 2x. Well, this is 100 minus 2x times 100 minus 2x plus 400x minus 8x squared, which is 10,000 minus 200x minus another 200x plus 4x squared plus 400x minus 8x squared. So that's minus 4x squared. The plus and the minus 400x's cancel out, and we've got plus 10,000 on the end. Let's define the area of card used to be y. So y is equal to minus 4x squared plus 10,000. This is a quadratic equation where a is negative 4, b is 0, and c is 10,000. So let's use our skills. A is negative, so it's a sad curve. C is 10,000, so when x equals 0, the curve cuts the y-axis at 10,000. B squared minus 4ac is 0 minus 4 times negative 4 times 10,000. That's 160,000. That's positive, so we'll have 2 real distinct roots. This means the curve cuts the x-axis in 2 places. But where? All along the x-axis, y equals 0. So let's put y equals 0 into our equation. 0 equals minus 4x squared plus 10,000, so 4x squared is 10,000, x squared is 2,500. So x is plus or minus the square root of 2,500, so x is plus or minus 50. Well, midway between x equals minus 50 and x equals 50 gives the coordinates of the maximum, so that's where x equals 0, here on the y-axis. So our curve looks like this. Obviously, in the real world, we can't cut negative lengths off a piece of card, and we can't have negative areas. So the only region that makes any practical sense is this bit here between x equals 0 and x equals 50. Well, what does the graph tell us then? If we don't cut any corners out, the area of the card used is 10,000 square centimetres. If we cut 1 centimetre corners, the height of the box goes up by 1 centimetre and the area goes down by 4 square centimetres to 9,996 square centimetres. If we cut 2 centimetre corners, the height of the box goes up by another 1 centimetre, but the area goes down by 12 square centimetres to 9,984 square centimetres. We can keep cutting an extra 1 centimetre off each corner until we go from 49 centimetres to 50 centimetres. That takes the height of the box, theoretically, from 49 centimetres to 50 centimetres. But the area of card used goes down from 396 square centimetres to 0 square centimetres. So to start off with, each extra centimetre we cut off the corners doesn't make a huge difference to the area of card used. But as we cut off more and more, each extra 1 centimetre we cut out of the corners generates a bigger reduction in the area of card used. It's an accelerating-y thing. Okay, let's recap what we've just talked about in this quadratics video then. 1. Graphs are a way of showing us what impact small changes to one variable will have on the outcome. They give us a picture of the relationship between inputs and outputs. 2. Quadratic equations have the general format y equals ax squared plus bx plus c. 3. Graphs of quadratics are symmetrical parabola. 4. Some quadratics are happy and smiley, while others are sad and negative. This depends on the value of a in the general equation. 5. The c in the general equation tells us where the curve cuts the y-axis. 6. The discriminant b squared minus 4ac tells us whether the curve will cut the x-axis in 0, 1 or 2 places. 7. We can set y equal to 0 and factorise to find out the x-coordinates of the point at which the curve cuts the x-axis, if there are any, and the numbers are nice. 8. We can set y equal to 0 and use completing the square to find out the x-coordinates of the points at which the curve cuts the x-axis, if there are any. 9. If we completed the square, it will also enable us to work out the x and y coordinates of the maximum or minimum point on the curve. 10. We can set y equal to 0 and use the quadratic formula to find out the x-coordinates of the points at which the curve cuts the x-axis if there are any. 11. We can use all of the above to help us sketch quadratic curves. 12. A sketch of a quadratic curve enables us to understand the effect of small changes in input values on real-life outcomes. If you're still awake, you should now be a quadratics expert and should quickly stop the video